Thank you for joining. Welcome to this Your Path to Deep Learning series. We have this series for workshop, which consists of 4 workshops, which cover different aspects of deep learning. And this, we try to take you over through fundamentals of deep learning and help you create your own models using frameworks such as TensorFlow and Keras. We have 2 workshops which were already conducted prior to this, on 23rd August and 25th August. So you can see the links on the screen, and the links will also be shared in the chat. So you can go ahead and watch these webinars if you're missed. And we have an upcoming one after today's workshop, that is on 1st September, which will be conducted by Fawaz and Asna. So you can go ahead and register yourself for the next workshop also. So we had some frequently asked questions. So we'll try to cover them up in the start so that everyone's clear with them. So all these sessions are recorded automatically, and the recording will be available on the same link instantly the session gets over. We also have these workshops available on different platforms such as LinkedIn, YouTube, Twitch, Twitter, and Periscope. So you can go ahead and you can watch the recordings on other platforms. Then, second thing, what is the prerequisite for the series? So we would require, if you have some basic understanding of programming and machine learning, that really helps in explain the concepts, and it will be easier for you to follow along. And next, we would require that everyone be registered and have your own IBM Cloud account. So if you have attended the workshops before, so hopefully you have registered and created your IBM Cloud account. If not, the link is on the chat. It is on the screen. That is ibm.biz/yourpath-to-deep-learning. Then, yes, there is a badge and certificate that will be given after the completion of the series. You need to register on coronary-class.ai for that. And you can over there you'll have to answer some questions, and you'll have a quiz. And once you pass the quiz, you should receive your the deep learning badge and certificate. So yeah, moving on. So some housekeeping for today. So if you're familiar with Crowdcast, we'll try to just brief over through it. If you've attended the previous sessions, so we'll just try to skim over through it really fast. So this on the top you have the session title, and you can click on the eye to get the information about the session and the speakers, and you can find out about the prerequisite and the links. Links are all over here. Then on the next side you have IBM Developer, so you can click on the green button to follow us so that you can get notified about our upcoming events. Then you have the chat section over here, which you can interact with attendees. You can see some some messages are being posted over there, so you can go ahead and put your message, interact with the audience. Then if you want to ask a question, there's an ask a question session. So you can go ahead, you can click on that, you can type down your question, and we'll try our best to respond to it as soon as possible. And then lastly, we have the workshop resources all stored for you in one link. So for that, you can just click on the screen button, that is Get Started on your screen. And once you click over here, it'll redirect you to the GitHub repository, which has all the links and all the resources for today's workshop. So today's session is based on language processing using recurrent neural networks with TensorFlow. With me, I have Karim Daif, who is an IBM client developer advocate in Egypt. And my name is Mridul Bhandari, and I'm an IBM developer advocate based in Dubai. So to get started, I would require you to register for an IBM Cloud account. So if you have already registered in the previous sessions, you can use the same cloud account, and you can reuse the same Watson Studio service you've been using in the previous workshops. So you don't need to create a new service. You can go ahead and go to this link ibm.biz/yourpath-to-deep-learning. And next we have the workshop, the GitHub repository for the workshop. You can also access this with the link in the chat, or you could click on the green button as I mentioned in the previous slide, and to redirect you to the GitHub repository. And lastly, we have all the slides which are going to use today stored on this link, and it will all be shared with you in the in the chat and in the follow-up email. So you can go ahead, you can access all the slides used in the session, and you can check out the slides, and you can cover up anything you have missed. And just to give you a heads up, this workshop might be 2 hours long because it's a very detailed workshop. So make sure to keep your water bottles ready with you. You have your water right next to you, because the session might go a bit long. Or if you're not able to stay for the entire session, you can always watch the recording. So as I mentioned, if you cannot stay for the entire session, we would require you to fill up the survey link that is shown on your screen. That is ibm.biz/ypdl-survey. So you can use your mobile cameras to scan the QR code also and fill the survey. It takes less than a minute to answer the survey, but it really helps us understand, how we could improve our workshops and what you want us to cover so that we can focus on that particular topic more than the other, so that we can deliver better workshops which are with content that is more interesting and more relevant to you. So the agenda for today, we are just going to be, going through what is deep learning, the deep learning architecture, then what are recurrent neural networks, or what is long short-term memory, what is TensorFlow, and why do we use TensorFlow, and what is the workshop use case for today. That will be conducted by Kareem Daif, and we're going to be sharing some helpful resources that might be interest to you if you're interested in learning more about deep learning. Yeah, moving on. So instead of me explaining what is deep learning, this was covered in the previous workshops. It would be really helpful if you could share what you think, and you could answer this question as what is deep learning, or you could explain in your words about your understanding about deep learning, ML, and AI in the chat. So I'll just wait for a minute to see the responses and to see, how who are attendees who have attended the previous workshops, how well they were able to, understand the concepts. Karim, could you go back to the previous slide? I'll just wait for a minute to see if anyone has anything to share. All right, so if you're not able to answer this, no issues. You can go ahead and you can catch up our previous sessions. Kamar has shared the links in the chat. So session 1 and session 2, we have covered this in deep. So I will not, really be going into really detail because it's all repeated. And we received a feedback that you wanted to focus more on the hands-on than the theory. So I'll just try to, summarize this for you in a line. Someone has already said it in the chat, so I'll just try to summarize it for everyone who's for all the other attendees. So AI is just a technique that enables machines to mimic human behavior, and ML is a subset of AI. So all ML is AI, but all AI is not ML. And similarly, all deep learning is ML, but all ML is not deep learning. So if you want to understand more in deep, you can go ahead and watch the previous sessions. This is I'm trying to keep it in short and so as to cater to your needs about focusing more on hands-on session. Yes, Kareem, let's move to the next slide. We do have some responses coming in chat. Yes, I think we have some attendees who have attended the previous session who are answering it correctly. So yeah, for the other attendees, you can go ahead and watch the previous sessions. So even this, the deep learning architecture, it was covered in the previous slide. So I'll just explain what we're going to be doing today. So we are going to be focusing on recurrent neural networks, and in recurrent neural networks, we're going to be specifically focusing on long short-term memory for use case. So I'll be explaining that. So if you want to understand more about convolutional neural networks, you can go ahead and watch the previous session that was based on handwritten character recognition using convolutional neural networks. You can go ahead and watch that session. And if you're looking to understand, the unsupervised learning or restricted Boltzmann's machines, you can go ahead and register for the next session. The next session, that is on 1st September, will be focusing on that. So what are recurrent neural networks? So recurrent neural networks is one of the foundational network architectures from which other deep learning architectures are built. So the primary difference between a typical multi-layer network and a recurrent network is that rather than completely being feed-forward connections, a recurrent network might have connections that feed back into the prior layers or into the same layer. So this feedback allows RNNs to maintain memory of past inputs and model problems in time. So RNN consists of a rich set of architectures. That is, one of the topologies we'll be looking into is long short-term memory. And the key differentiator is it is a feedback within the ARC network. So this could help manifest itself from a hidden layer and the output layer, or some combination of that. So it keeps reiterating over and over again. So RNNs can be unfolded in time and trained with standard backpropagation or by using a variant of backpropagation. So that is why it is also called backpropagation in time.
Hi guys. So I think it's just Mustafa. Are you with us? I think Mirdul just dropped. Mustafa, are you there? Hello. Okay. So yeah. So sorry. I think we just had an internet connection problem with Mridul. But I think Mustafa's still there. Mustafa, can you hear us? Yeah. So basically, I'll try to continue until Mridul comes back. Oh, there he is. Hello, Mridul. You're on mute, Mridul.
Hello, hello,
Yeah, we can hear you now. No
hello.
problem. Yeah, we can hear you.
Kareem, can you do?
Yeah,
Kareem, Mustafa, can you hear me?
yeah, we can hear you. We can hear you.
Okay, I'm not able to hear Kareem. I think so. There's some issue.
Mustafa,
I'll
can you
just
hear
refresh
us?
again.
Okay, so sorry, you can hear Mridul and Kareem. Okay, thanks, Kumar. So Kumar, please just let us know if you can't hear. And I think Mridul is just reconnecting. So sorry about that, guys. So let me just go back a page.
Hello.
Um, yeah, hey, Mridul.
Yes. So I see in the chat, so you can hear me.
Yeah,
Okay. All right.
perfect. Go ahead.
So uh, I'll 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 just. Do you want me to recap the previous slide, or what part was I cut off on? If you can share that so that I
I
can
think
repeat
we're good.
that.
I think you just continue the slide. I think we're good. Yeah, no problem.
So the advantages of using RNN, it captures the sequential information present in the input data. That is dependency between the words in the text while making predictions. It can also share the parameters across different time steps. So this is popularly known as parameter sharing. And this results in fewer parameters to train and decreases the computational cost and time. Now, there are also some challenges with recurrent neural networks. So it's deep recurrent neural networks suffer from the vanishing and exploding gradient problem, which is a common problem in all the different types of neural networks. So that is why we come to this topology in recurrent neural networks, that is the LSTM, the long short-term memory. Kareem, if you can hear me, can you go to the next slide?
Yeah, Mridul, I'm on the next slide. Are you there?
Yeah, I can hear you now.
Yeah.
I think so. We're having internet issues. So I think everyone wants us to go to the previous slide. Kareem, could you go back to the recurrent neural network slide? Sorry. Okay. Are you on the slide? Because for me it shows it's the next slide, the GIF slide.
Okay, so I hope you guys can see recurrent neural network on the page. What time is it? Okay, so I guess there's something. So here,
Hello.
yeah, I
Hello.
hear you. Yeah, I hear you, Ridu. What slide do you see now? Yeah, Mustafa, are you with us? Mustafa, can you hear us?
Yes, Kareem, I can hear you. What's the problem?
Mustafa?
Yes, can you hear me?
Yeah,
Hello?
Mustafa, I can hear you. Mustafa, can you hear me?
Yes.
Yeah, I
What's
can
the
hear
problem?
Ridu, but I can't hear Mustafa.
Okay, Karim, I can hear Mustafa. It's fine. So let's continue with the slide. We'll be sure we are already lost a few minutes. So hi everyone. We are back again. Really sorry for that delay because we have experiencing some internet issues. So you wanted us to cover the slide on recurrent neural networks. So I will try to go over through this. really fast. So as I mentioned, recurrent neural networks is one of the foundational network architectures from which other deep learning architectures are built. The primary difference between a typical multi-layer network and a recurrent network is that rather than completely being feed-forward connections, uh, a, a recurrent network might have connections that feed back into the prior layers or into the same layer. So this feedback allows RNNs to maintain memory of past inputs and model problems in time. RNN consists of a rich set of architectures. We'll be looking into one of the popular topologies in the next slide, that is Lstm. Next, and the key differentiability is the feedback within the network. So this could manifest itself from a hidden layer, the output layer, or combination, or some combination of these two. So RNNs can be unfolded in time and trained with standard backpropagation or by using a variant of backpropagation that is called backpropagation in time. So some application examples of recurrent neural networks include speech recognition and handwriting recognition. So the advantages of using recurrent neural networks is that RNNs capture the sequential information present in the input data, that is dependency between the words in text while making predictions. As this is mainly used in speech recognition.
Sorry, I think Karim has some problem connecting.
Yeah.
I think he'll be here in a second. Sorry everyone. Sorry for this connection problems. Yeah, we have Karim again. Thank you, Karim. Can you hear me now, Karim?
Yeah, I can hear you.
Yeah.
Okay.
So Karim, we can move to the next slide. I've covered this slide. So okay, so I'll just repeat this topic again. So the advantages of recurrent neural network is that it captures the sequential information present in the input data. So as it is mainly used for speech recognition and which language, with natural language, the dependency between the words in making in the text while making predictions, it's very useful for that because it's able to capture the sequential information present in the input data. So you can see at each time step depends not only of the current word but also on the previous words. So this is really helpful in these cases. And the other advantage is RNNs share the parameters across different time steps. So this is popularly known as parameter sharing. This results in fewer parameters to train and decreases the computational cost and reduces the computational time. And this makes it really efficient. So there are some challenges with recurrent neural networks also. So deep recurrent neural networks, the recurrent neural networks with large number of time steps, suffer from the vanishing and exploding gradient problem, which is a common problem in all different types of neural networks. So that is why we have this new topology in deep recurrent neural networks, that is LSTM. So LSTM RNN couldn't hold the context for a long sentence. That is why a long short-term memory was created. So could you move to the next slide? So yeah, just a minute. So LSTM, that is long short-term memory, was created in 1997, but it has grown in popularity in recent years as an RNN architecture for various applications. So you'll find LSTMs in products that you use every day, such as smartphones. Even IBM uses it for its IBM Watson products, and it has achieved a milestone, setting conversational speech recognition by giving better results in these recognition patterns. So the LSTM departed from typical neuron-based neural network architectures uh, and instead introduced the concept of a memory cell. So the memory cell can retain its value for a short or a long time as a function of its inputs, which allows the cell to remember what's important and not just its last computed value. So the LSTM memory cell contains 3 gates that control how the information flows into or out of the cell. The input gate controls when new information can flow into the memory. The forget gate controls when an existing piece of information is forgotten, allowing the cell to remember new data. Finally, the output gate controls when the information that is contained in the cell is used in the output from the cell. So the cell also contains weights which control each gate. The training algorithm, commonly known as backpropagation, optimizes these weights based on the resulting network output error. So this is how long short-term memory works. Karim, can you move to the next slide? So the next thing, before we go ahead, actually I would like to cover something. What is the advantage of using RNN and CNN? That was one of the questions that was asked. So RNN, CNN, is convolutional neural network, that is more fit for spatial data, that is images, whereas recurrent neural network is more for temporal data that comes in sequences. And convolutional neural networks employ filters within convolution layers to transform data, whereas RNNs reuse activation functions from other data points in the sequence to generate the next output in a series. Convolutional neural networks take a fixed size of inputs and generates fixed size of outputs, whereas recurrent neural networks can handle arbitrary input and output lengths. So it does not have to be fixed length for the input and output. And CNN is a feed-forward neural network that is generally used for image recognition and object classification, while RNNs works on the principle of saving the output of a layer and feeding this back into the input in order to predict the output of a layer. And CNN considers only the current input, while RNN considers the current input and also the previously received inputs. It can memorize previous inputs due to its internal memory. So if you were confused between what is CNN and RNN, this is just to help you differentiate between the two. So next, we are coming to what is TensorFlow. So TensorFlow is an open source end-to-end platform for creating machine learning applications. It is a symbolic math library that uses data flow and differentiable programming to perform various tasks focused on training and inference of deep neural networks. It allows developers to create machine learning applications using various tools, libraries, and community resources. So it is currently the most famous deep learning library in the world, and it is developed by Google. So even Google products use machine learning and use this TensorFlow in all its machine learning applications and in their products. And you can see the example of this in your Google search engine. So every time you type a word, it tries to predict the next word for what would be the next word. So that's why because Google uses experience a faster and more refined search with due to the help of TensorFlow. And it tries to take advantage of the massive data sets it has from the users, and it tries to give them the best experience back. So yeah, Kareem, can you move to the next slide? So why do we use TensorFlow? So TensorFlow helps in easy model building. It helps you in creating robust ML, production level ML products anywhere from the world, and it supports both CPUs and GPUs. So that's why it's supported by most of the computing devices. So it becomes very easy for developers to experiment with this and utilize this library in their products. And it is very easy to scale from research to production with the help of TensorFlow. Yes, moving to the next slide, Kareem. So next we have the workshop use case. This will be handled by Kareem. So in this, we'll be trying to apply recurrent neural networks, more specifically Lstm, for language modeling. So we will create a recurrent neural network model based on long short-term memory unit to train and benchmark the Penn Treebank dataset. And we'll be using Watson Studio, Jupyter Notebook, and TensorFlow. So if you attend the previous workshops, you can utilize the same Watson Studio service which you have created in the earlier sessions, and you can just go to that service and open up. And now I'll be handing over to Kareem to take you through the hands-on session.
Thanks, Mridul. Hi, everybody. Welcome to our crowdcast. So I'll be doing the hands-on part. So let me just escape out of this. Okay. So basically, you have the link in the chat. This is basically the IBM Developer Mia GitHub org, and we have this repo called YPDL, Recurrent Neural Networks using TensorFlow Keras. So this is what we'll be going through today. Basically, we'll just talk about the first section is what is language modeling. So language modeling, basically, like it says here, it's the task of assigning probability to sequences of words. So if you have this is N, and what's the best word that fits after that? So based on context and many other factors, you would probably see that example. This is an example would be the best prediction for the next word. After that, so basically, this kind of analysis is very, very important for speech recognition, machine translation, also for image captioning and text correction. So here in this chart right here, let me zoom in for you guys. In this diagram right here, so as the above image shows, RNNs, models fit this problem like a glove, along with long short-term memory and its capacity to maintain the model state for over 1,000 time steps. We all have the tools we need to undertake the problem. So the second task here is pretty much the data set. So, you know, machine learning in general, it needs input to train. It needs data to train. So we're using the Penn Tree data set. So it's called Penn Tree because it's from Pennsylvania University. It's the Treebank data set. You can find that on many places. If you go on the internet and just type Penn Tree, you'll find that. And this is the UPenn, University of Pennsylvania.
Karim,
Yep.
Sorry to interrupt you. Could you zoom in a bit?
Yeah, sure. I'll zoom
Just
in.
to read your screen. Yeah, thank you.
Yeah, no problem. Thanks, Ritu. So yeah, so here's the University of Pennsylvania. This is the Penn Tree book, and what is it in essence? I think this is a really good. There's a really good document here that talks about it. So it's over 1 million words from 1989 Wall Street Journal materials that are annotated. So they've been annotated. They've been annotated, humanly annotated for syntactic annotations. So that's our data set. So the Penn Tree data set is big enough for natural language processing, and it has a large amount of data that's annotated and corrected by humans. So that's our input. That's our data set. Section 3, we talk about word embedding, which I think in the other series, if I'm not mistaken, it was discussed. So what is word embedding? So for better processing, in this tutorial, we'll make use of word embeddings, which is a way of representing sentence structures or words as n-dimensional vectors of real numbers. And the word embedding tends to group up similar words reasonably together. So we can group these words, which all reference quantity, like 5, 4, 7, bunch, like a bunch of flowers. These are all grouped together as being number-related words. And on the right-hand side, you can also have country-related words like US, France, Italy, Germany, economy-related as well. So this is how basically there's grouping of words. So as you can see, words that are frequently used together in place of each other or in the same places as them tend to be grouped together. So in section 4 here is where we'll actually start building the LSTM model. But what I wanted to show you here is how to pretty much set it up. So I'm sure you all have a Watson Studio instance, and you create in it a Jupyter notebook. And once you have that Jupyter notebook, it would look like this. This is the notebook. And here we're at this section here. So building the LSTM model. Okay, so all we do first is that we import TensorFlow. So we do a pip install. We install TensorFlow and then NumPy as well. So we install them, very straightforward. We just do a check that we have the right version of TensorFlow. After that, we pull in a script, a Python script called reader. We just do a wget, we pull that in. We import the reader. And then the next step is we import the data set. So there's a simple example data set that we do a wget, we pull that in, we unzip that into a data directory. And then of course one of the key pieces of machine learning or AI is hyperparameters. And here we have a list of hyperparameters. So we have the initial weight scale, the initial learning rate, and many other hyperparameters. The batch size, so 30, and so on. So in terms of the network structure here, so in this network, the number of LSTM cells are 2. To give the model more expressive power, we can add multiple layers of LSTM to process the data. The output of the first layer will become the input of the second, and so on. And that's basically where you have your forward looping approach to AI. The recurrence step is set to 20. That is, when our RNN is unfolded, the recurrence is 20. So that means that we have 2 hidden layers. So the structure is we have 200 inputs, 200 times 200 for the weight, 200 hidden units, and so on. That's the network structure. The input layer here is the network has 200 inputs. So we suppose that each word is represented by an embedding vector of dimensionality of E equals 200. So the input layer of the cell will have 200 linear units. And then we have the hidden layer, which is each LSTM has 200 hidden units, which is equivalent to the dimensionality of the embedding word. So there's a lot to be done and a ton of information, but basically this is now where we start the training data. So we need to look at the training data, and I think Kamar mentioned to me that in the other workshops that you've probably attended, you've already gone through this, how you can divide the training data into separate pieces. One is called, so you read the data and separate into training data, validation data, and testing data. So that's what we are doing here. We check the size of the training data. It's almost 1,929,000. We have here just a simple print of the first 100 training data. So that's all we do. We just call this function just to show us what the training data looks like. It looks like this. And now let's just read one mini batch. So we know the batches are of 30 or so on. So we're reading in a mini batch. We shape that data. And then after that, we basically print the first 3. And that's pretty much what's happening here. Then we have the embeddings. So the word embeddings, or the embeddings that we talked about. So we have to convert the words in our data set to vectors of numbers. So we need to work with numbers, right? Because it's all based on matrices. So we need vectors of numbers. So the traditional approach is to use one hot encoding method. And I think Kamar as well said that in the other workshops, you weren't using word to vec. You were using the TF-ID approach. So this is using the word to vec approach. So the embedded vectors also get updated during the training, and we create the embeddings for our data, the embedding vocab, which is a matrix. So here we use Keras here to do the embedding. We define where to get the data for our embedding from, which is of course from the input data. This is where we get the numbers now, the word to vector. Then we start constructing the neural network. So we're using a stacked RNN here in Keras. So it's a stacked RNN cell, which is a 2-layer LSTM network, because we know we're dealing with 2 layers like we discussed previously. So here we take we run the stacked RNN cells here with the two LSTM cells. The next is the input should be a tensor of shape. So batch size, maximum time, embedding vector. So in our case, it's 30, 20, 200. So now we want to initialize the states of the network, which is what we do here. We initialize the RNN here. Yeah, and F, to respond, you can get this notebook from the link. So that link that was provided is to our GitHub. And yeah, you're right. So I went in too deep. So here, this is the link that was provided to the GitHub repo. It shows you here how to set up Watson Studio, which I'm sure you've already done that already. Create a Watson Studio. To go to our Jupyter notebook, you just go to notebooks, and inside you get the recurrent neural network. So I hope that answers the question, F. So it's inside the Git repo under notebooks. So back to here. So now we specify basically the initial state. So we need zeros here. We need the initial state. We need to flatten it. right? So the initial state, so for each LSTM, there are 2 state matrices. No problem. C state and M state. So each hidden layer has a vector size of 30, which keeps the states. So for 200 hidden units, we have a matrix of 30 by 20. So we just zero value them here. We set them. Yeah, so Savine, that's right. So 2.20 RC0, that's been updated because, it's hard to keep, pip or Python, the stuff keeps upgrading. So the minimum now is RC1. Just add RC1, 2.2.0-RC1, and I'll show you that. Or I can scroll up if you want to see. I'll scroll up. Sorry, guys, just for Savine. Just you can, if it doesn't work for you with that version, just switch it to 2.2.0 RC1, and you should be okay. All right, so we're just we're in the initial state now, the all zeros, which is over here. So we set the initial state here to all zeros. So let's look at the output. So the output of the stacked LSTM comes from 128 hidden layers, and each time step is 20. One of them gets activated. We use the linear activation to map 128 hidden layers. So now we pass the inputs to the layers, and then we get all the outputs here. So 30, 20, and 128. Okay, good, Savine. Yeah, so sorry, there was just, it's a little bit, the stuff always changes with pip. So the oldest TensorFlow is now 2.2.0 RC1, resource candidate 1, and not RC0. So that's just a little mistake here. I'll update it here in the GitHub as well. Yeah, so then let's look at the dense layers. So now this is one of the key parts of also machine learning is we need to create densely connected neural network layer that would reshape the output, because we want to reshape that output. We're basically playing around with the matrices, right? So we have a 30 by 20 by 128. We need to convert that to 30 by 20 by 10,000. So that's where we set up the dense command. We set up the dense, and then we print that out, and we see that it's by 10,000. Then we have the activation layer. So one of the most popular, and I remember Mustafa 2 years ago is the one who actually explained this to me, our moderator. So you have the activation layer softmax. So that's one of the most popular activation layers. So we use softmax as the activation layer. It's also then applied to derive the probability of the output being in any of the multi-classes, in any of the 10,000 possibilities. So this is in machine learning, you have what's called an activation layer. So let's look at the probability of observing for t equals 0 to t equals 20. When we run that, we'll get basically what is the, so here we'll get this data and then the prediction. So what is the word corresponding to the probability output? Let's use the maximum probability. So here in NumPy, we do the argmax of the output words. And then we get, so what is the ground truth for the first word of the first sentence? You can get it from the target tensor. So if you want to find the embedding vector, which would be at position 0. And then in terms of objective function, which I think also Kumar mentioned, it's basically what you could call the loss function as well. So in the other workshops, so that's our objective function or the loss function. So just in 1 second, just so you understand, like diminishing returns. So what's the loss? So now we have to define our objective function to calculate the similarity of predicted values to the truth, the ground truth, and then penalize the model with errors. So our objective is to minimize the loss function. That is to minimize the average negative log probability of the target words. That's what's called the objection or loss function. So we're using here cross entropy here to do that, to specify, to return the loss. After that, we need to define a cost as the average of the losses. So what's the cost? What's the loss amount? We do a loss over the batch size, which we know the batch is, I think, 30 in our example. All right, so now we kind of just talking it from the outside. Let's look at now the building the model, building the training portion of the model. So to do training for our network, we have to take to do the training for our network, we have to take the following steps. We define what's called an optimizer. So that's basically the learning rate. So here, defining the optimizer, that's the learning rate. So we use SGD from optimizers of Keras, and it's the maximum gradient norm, max grade norm. That's our optimizer. Then we have to assemble the layers to build the model. So that's pretty straightforward here. We have our layers, it's sequential. We have the first layer is the embedding layer, the word embedding, then the layer themselves, the density, the activation, the loss, and then finally the summary. Third is we want to calculate the gradients based on the loss function. And fourth, we want to apply the optimizer. So let's look at calculating the gradient. And the trainable values. So I guess that's all here. The trainable variables here, when defining a variable, if you pass trainable true, so that tells TensorFlow that this model is trainable. So, and you get extra parameters from that, variables from that. So the variable constructor automatically adds new variables to the graph collection, trainable variables. Now using TensorFlow TF trainable variables, you get all the variables that were created with trainable true. So this gives you more variables for your training. We can also find the names of these variables that are available, which are embedding, kernel, recurrent kernel, bias, and so on. And then this is the third one that I was wondering where that went. So the third one, which is coming from here, calculate the gradient loss, the gradients based on the loss function. So here is where we calculate the gradients based on the loss function. So the gradient of the function is the slope of its derivative line, or in other words, the rate of change of a function. It's a vector that points in the direction of the greatest increase of a function and is calculated by the derivative operation. And this is the formula here. First, let's recall the gradient function. And then we basically set that up exactly like that. So constant 1, constant 2, gradient tape. And the g.gradient function allows you to compute the symbolic gradient of one tensor with respect to one or more other tensors. And this constructs the symbolic partial derivative of the sum. Okay, again here it's more of the gradient function itself, and this is basically the gradient for all the variables here, and we get our loss. And then here is where we can print out the gradient loss is here, that's printed out here. And now we have a list of tensors. We can use it to find clip tensors. Clip by goal norms, values of multiple tensors by the ratio. So clip by global norm, an input and it returns 2. So we have a list of clip tensors called list clipped and the global norm of all tensors. So here we define the gradient clipping threshold. Again here, we run the clip by global norm of TensorFlow. We get that, we get basically the gradients. And after that, we apply the optimizer that we talked about previously. We're just basically applying the optimizer to the variable, to the gradients tuple. And tuple is basically just buckets like an array per se. So that's what we call a tuple. So we create the training data set operation. So now let's create a class. So now we get to actually running this training model. So we create a class for the LSTM model. So we've learned how the model is built step by step. Now let's create a class that represents our model. So we have to create the model in accordance with our hyperparameters. We have to create the LSTM cell structure and connect them with our RNN structure. We have to create the word embeddings and point them to the input data. We have to create the input structure for RNN. We need to create the logistic structure to return the probability of words. And we need to create the loss and cost functions for optimizers to work. Then we create the optimizer. And finally, we need to create a training operation that can be run to actually train our model. So this is kind of the core piece. So here, class PDB model. and that's the Penn Treebank. That's where, if you remember, that's PDB, that's what it stands for. So this is the Penn Treebank model. This is the actual class for the model itself. So here, this is the constructor, the initialization in Python here. We set our parameters, which are the parameters we saw above. We just specify them here. We put them at the beginning just for ease of use. We initialize the model. So here, models.sequential. This is initializing the model. We create the word embeddings layer and adding it to the sequence here. And we create the embedding for our input data. And the size is a hidden size. We create the LSTM cell structure that we saw before. This creates only the structure for the LSTM and has to be associated with an RNN unit. So this is where we set up the two LSTM cells, the two layers. By taking in the LSTM cells as parameters, the stacked RNN cells function junctions the LSTM units to the RNN units. This is now kind of joining together the LSTM units to the RNN units, which is we're using here the stacked RNN cells that we saw before. So now we need to create the input structure. So kind of the placeholder. So the input structure is a 20 by 30 by 200. And we consider each word is represented by a 200 dimensional vector. And we have 30 batches. We create 30 word vectors of size 30 by 2000. The input structure is fed from the embeddings, which are filled in by the input data. So we have two steps. The first step, the first word of each of the B sentences. In step 2, the second word of each of the B sentences is input in parallel. And parallelism is only for efficiency. So each sentence in a batch is handled in parallel, but the network sees one word of a sentence at a time and does the computation accordingly. So here we instantiate our RNN model and setting the stateful to true to feed forward the state to the next layer. So this is basically where we set the stateful to true, and this is now how we have a forward propagation or forward loop. So that means that each new layer is using the output from the previous layer, which is very good for increasing the prediction. Define the initial state. So the model state for the very first data point. It initializes the state of the LSTM memory. The memory state of the network is initialized with a vector of zeros, like we saw before. So we basically just set it to zeros here, just kind of clear it in a way, and we set it as the initial state. Then we add the RNN to Keras, so we add this RNN layer to our model, and then we instantiate the dense layer. So we add here the dense layer that we saw, which is from that connects the output of the vocabulary size. And then we add our activation layer, which we know is softmax, and deriving probability to each class and adding the layer to the model. So now we're just adding that layer, and then the activation layer. And then we add the optimizer. So as stochastic gradient descent, optimize SGD, and it's using max gradient norm here. Then we just compile. So we compile and summarize the model stacked up using the Keras sequential API. This is the compile. This actually builds the model, compiles the model, produces a summary. And then we have our cross entropy function that we talked about before. And now we have the actual training of the batch. So you create the training operation for our model, where you get all the tensor variables marked as trainable. And then we basically define the gradient clipping threshold. And this is pretty straightforward here. We just loop through and we basically get the gradient of loss. And we define the gradient clipping threshold. We create the training TensorFlow operation through our optimizer. Then we run the test batch. This function here is actually where we do our testing. So we do the testing. So we create the testing operation for a model, right? It needs training. It also needs testing, right? So we pass in an example, a word, and it tests. It gives the prediction. All right. So with that, the actual structure of our RNN with LSTM is finished. what remains for us to do is to create the method to run it. So we need the run epoch method to be run at each epoch and a main script which ties all of this together. So what our run epoch method should do is take our input data and feed it to the relevant operations. This will return at the very least the current result for the cost function. So here we run one epoch. Yeah, go ahead.
Could you zoom in a bit more? It's tough for people to read.
Okay.
All right. Thank
Is that
you.
better? Yeah, no problem.
Yeah,
Okay.
it's better for me at least. I hope. In the chat, you could let us know when if it's not, if you're not able to read.
Okay.
If it's fine now, just let us know. I'll let you know once they let me know.
Okay. Thanks, Rido. All right. So we basically, what our run epoch method should do is, we talked about that. So at the very least, you got to return the cost function. Then you know that that iteration, that epoch didn't really do anything. It was equal to your cost. So basically, that's what's happening here. You're running it in iterations, and at the very least, you should improve. It should improve, and we'll see that right now. So run one epoch. It takes as a parameter the model instance, the data to be fed, training or testing mode, and verbose. So here, this is the run one epoch. We define the epoch size. So for each step and data point, we iterate through, we evaluate and return cost, state by running cost, final state, and the function. So here, if it's training, the loss is training batch, and else, if it's not training, the loss is test batch. So we add the return cost to costs. We just add to costs and add the number of steps to the iteration. And we just print perplexity. And perplexity, we know, this is where I'll go to the very top because I did skip this word in case some people don't know what it is. I mean, before this, I wasn't really familiar with it myself. So perplexity here, perplexity is a really important term here. So here, should be here somewhere, yeah. So for language modeling problems, perplexity is the way to gauge efficiency, to measure efficiency. Perplexity is simply a measure of how well a probabilistic model is able to predict its sample. A higher level way to explain this would be saying that low perplexity means a higher degree of trust in the prediction. So therefore, the lower the perplexity, the better. So that's what we're trying to do. We're trying to get the lowest possible perplexity, which means that's the highest confidence. So we'll go back to where we were. Perplexity. So then we print out the perplexity and the speed, and we run that. And then we have the training, validating, and testing of the model, and we're almost done. This is the last piece, guys. So sorry, 53 is the last piece. So I know it's a lot of material, but it's a really nice example, I think. So training, validating, and testing, is it similar to accuracy? Yeah, perplexity, you can say, is inversely correlated. So the lower the perplexity, the higher the accuracy. And I think more in machine learning, we're predicting. So it's kind of, the confidence of the prediction. Accuracy to me is going to a source of truth. But this is all we're predicting. We're trying to take guesses. So the more we're sure, the more we're confident about our guess. So the lower the perplexity, the higher the confidence in the prediction. Yeah, no problem, Adir. All right, so training, validating, and testing the model. So finally, we can create the main method to tie everything together. The code here reads the data from the directory that we got the samples for the Penn Treebank, that small sample with the wget that we unzipped in the data directory. And we use the reader helper module that we did also a wget to it. And then we train the model and evaluate the model on both a validating and a testing subset of data. So you use data that you know the result of, that's your validating, or sometimes called your reference data. So you know that the outcome what it should be, and if the outcome is what you want, then you know that your model is pretty good. Then you use testing subset, stuff that's unknown. You want to really do predictions. You do your testing subset, and then you see the results. So that's what's meant here by both a validating and a testing subset of data. So here we're just reading the data, straightforward reading in from the data directory. We read that. And then we basically go through this. Before I talk about this, I want to show you the output so that this makes more sense. So what happens here is when we actually train the model, when we start running this, we'll get the model, the layer, and we'll get the epoch. The learning rate is 1. We have, like we saw before, 1549. We have 1,500 iterations. Perplexity is very high, 4,000. That's very big compared to what's under 1,000. And we want a smaller number. We see the perplexity is going down. We see the speed is how fast it's reading words per second. So in each iteration, we know that they're big batches. In the iterations, we see that the perplexity keeps going down. Now it's at 200. Then we have our second epoch, and our second epoch, the perplexity is also going down to 160, and so on. When we look at the very end, it's epoch 15, I think. Yeah, at epoch 15 here, the learning rate is 0001, and the perplexity is very low now, 67, 55, 52, 51. So as you can see, the model's perplexity ratings drops very quickly after a few iterations. It means it's getting smarter. It's getting more confident of what the results will be because it's a feedback loop. These epochs are feeding to the next layer. So as we elaborated before, lower perplexity means that the model is more certain about the prediction. And now let's just look at the code that does this piece. Yeah, so here, all we do here is we just import the time. So epoch is just a time. So I think epoch technically means like, I think from January 1st, 1970, that's like what's called epoch time or so on in computer lingo, but it's just a reference of time. So it's a reference, epoch just means time here. So we instantiate PDB model class, which we saw before that we did. We have that PDB.instance that will run the init function, the init method inside it. And then we do keras backend, and this is now where we do our for loop here. So we define the decay for this epoch, how much it will go down, so that's the decay. And then we have our optimizer here. We run the loop for this epoch in training mode, and then and that's why it's the training data here. Then we run this loop for this epoch in the validation mode, which is the valid data. And then we run the loop in the testing mode, which means this is the actual test data to see how effective was our training. And then we print the test perplexity and total time taken. So let's look at test perplexity and total time taken here. So I recommend when you run this over here somewhere, you can increase the environment. If you click on this environment, I use 2 CPUs. I think the documentation says use 4 CPUs. You should increase that to 4 because it'll make it a lot faster. Because for me, it took a long time, but I just wanted to see how it would work with 2 CPUs. So it does work, just takes a really long time to run it. But you see the test perplexity is 116. So that means of that test data, we've got a perplexity of 116. And that's really your criteria, A better model with the same test data should give you a lower perplexity. And that's how you can kind of measure the models. So again, this is all coming. There are more links here if you want to know more about IBM and Watson products. So the gentlemen that created this are Walter Gomez and Said. So I think they did a really good job, and it's updated for TensorFlow 2 by Romeo and Samaya. So you can see that here, and this is all again from our GitHub repo. And if someone didn't create it already, So it's very easy to create an IBM Cloud account. Once you go to IBM Cloud, you just click Watson Studio here. You get a Watson Studio service. And in Watson Studio service, you create what's called a machine learning instance. So here you create a machine learning instance. And after that, you create a cloud object storage. You create an object storage. So you need like 3 things: Watson Studio service, machine learning service, and a cloud object store, a cause service. That's to store the data sets and stuff. And then you basically, you're inside IBM Cloud Pak for Data, which is kind of the new term for Watson Studio. It's bundled as IBM Cloud for Data. You just click Add Projects, Notebook. Once you click Notebook, then you get to this page. And you just have to put your notebook URL here, which is the URL to our notebook, which is inside Notebooks. Inside Notebooks, this is the notebook. Okay, so I hope this wasn't really too fast. I'm just trying to, you can watch the replays, and it should be pretty clear, I hope. And I think this is really good, a really good example to learn about natural language processing, NLP, to kind of understand that you can actually predict what the next word is going to be based on a large corpus. You know that Penn Tree has millions of articles and stuff. So it's nice. You can use deep learning to know from a few words probably what the next word will be. And that's what's used in a lot of, like, we know, speech recognition, because speech recognition doesn't only listen to the acoustic model or the acoustic, what you say. It also bases it on what you said before, so that it can kind of be more confident of what word you said. So what you said before helps a lot to know the word that you just said. So for example, the word example. So that's kind of how we use NLP and LSTMs. And like Spiciso said, like Mridul said, that LSTM, one of the good things about it versus straight RNNs is that it handles long sentences. So with longer words, because it has a short-term memory. You have an area where you can where it stores the previous state. And that's it. So Amit, so how CPU intensive is it? Yeah, it's pretty heavy. I ran it locally though on an iCore 7, like kind of a medium range machine for these days. And if I have it open here, it didn't take too long. So you can run the exact same example on your computer at home, but I really recommend you do it on IBM Cloud, so that you can kind of get to learn a lot about Watson Studio. But since it's a Jupyter notebook, it can run. It took here like 577. This is how many seconds? It's like, I don't know, 2 hours or 3 hours or something to run. But you could run this all locally. You can run everything locally. So here, like on my computer, it took, I think, here it took a total of 5,700 on, say, an iCore 7 seconds. And here on two CPUs, it took, I think, the same amount of time. So you can see that these 2 CPUs are like Xeon processors, or really strong chips. So I really recommend you do it on IBM Cloud. You'll see here how many seconds it took. It took about 5,000 as well. Oh, 2,000. No, 20,000. No, it actually took longer. So I didn't look very carefully at the numbers, 20,000. So I really recommend you use like 4 CPUs rather than 2, and so on. Yeah, no problem, Amit. But try it out. Definitely try it out on IBM Cloud. It'll be a lot easier. There's a lot of stuff to run it locally, and it's really kind of, our workshop is to kind of just introduce you to machine learning and deep learning, but especially on IBM Cloud. So give it a try, and you can always increase the CPUs, and I think it's free up to 4 CPUs or something. All right, so over back to you, Mridul. Thanks, everyone.
Yeah, Karim. Oh yeah, will you share the slides? Yeah, could you move to the next slide? Hello. Karim, you're on mute if you're speaking.
Mridul, we can hear you, bro. You can go ahead, please.
Sorry?
We can hear you.
Yeah, it's good. We're ready. Go ahead.
Yeah. Yeah, can you move to the next slide? Yeah, so this was the hands-on session. So if you aren't able to follow, you can always go onto IBM Cloud account. You can go to this website. You can create an IBM Cloud account using this link, that is ibm.biz/your path to deep learning. And the GitHub repository link is shared by Kamal and Fawaz in the chat, so you can always go and access the GitHub repository. The notebook is stored over there. And over here, we have the QR code with the survey. So you can go ahead, you can scan this QR code using your phone cameras. You can scan it, or you could go to this link, that is ibm.biz/ypdl-survey. And you can go ahead and you can fill the survey, and you could let us know how we did this workshop and how we could improve, and what you disliked or liked about this workshop. So you can go ahead, you can also give your suggestions on what we could cover next, that we'll focus on those topics which are more interesting and relevant to you. So to summarize what happened in the hands-on session, we used a Penn Treebank dataset as explained by Kareem, and then we went over through what are word embeddings, and then we built an Lstm model for language modeling, and then we trained, validated, and tested the model which we had built using Lstm. So there are some useful resources which we'll be sharing with you in the chat and in a follow-up email. So you can go on to these resources and you can, expand your knowledge on deep learning by going to and doing this course on Introduction to Deep Learning. That the link is there on the screen and will be shared in the chat. And then we also have a neural network playground, so you can try out TensorFlow, you can play around with it, and you can see how nodes work. It's very interesting UI. So you can go ahead, you can try that out, and you can understand how it works. And then we have a course on neural networks and deep learning on Coursera. So you can go ahead and you can do this course and you can learn more about neural networks and deep learning. And to secure your badge and certificate for after the series, you can head over to cognitiveclass.ai. You can log in and sign up using your email, and then you need to search for this course called Deep Learning with TensorFlow. You can enroll into the course and you can complete the review questions. So each module, it has 4 modules, and we are doing that as 4 sessions. You can go ahead and you can go ahead and answer those questions after you do these sessions. And you will be, once you complete the final quiz, you will be able to secure the deep learning badge and certificate. And you can also join a Slack community. The link is ibm.biz/ypdl-slack. So you can go ahead, you can join this community, and you could interact with other attendees who have joined this workspace on Slack, and you can share your questions and any resources you come across which you find useful with other attendees. So you can go ahead and you can share your knowledge, and you can also interact with other people, interact with other developers around the globe using this community. We'll share all of this in the chat. And then we want to say a big thank you to our partners to help us conduct this workshop and make it a success. So thank you all to all the partners. And then we have an upcoming workshop in the series, that is the final workshop that will be conducted by Fawaz Siddiqui and Asna Javed. So this will be conducted on 1st September, that is 6 p.m. On GMT +4. So this will be based on personal recommendation engines with TensorFlow. So you can go ahead and register yourself for the workshop, that is crowdcast.io/e/ypdl-4. It's the same link as today, just the 3 becomes 4. So you can go ahead, you can register for yourself for this workshop. And you could, once you complete this, you can secure your badge, the final badge and certificate. Yes, and then that brings us to the end of the session. Thank you for joining us today. And if you have any queries, you can reach out to us. These are our details. I'll share all the details, all the links which I've mentioned in the chat. So we'll give it a few minutes, and you can go ahead and you can share your questions and anything in the chat, and we'll keep an eye on that. Until that time, I'll just share all the links which I've mentioned in the chat.